Hi everyone, welcome to the fifth lecture of this module 10, where we are talking about displacement sensors and accelerometers or acceleration sensors. So, this is essentially the third lecture on accelerometers, and in the previous class we were discussing about thermal accelerometers. So, we have seen that these thermal accelerometers are mostly of two types. One is heated plate accelerometers and another is heated gas accelerometers. And in the previous class we have talked about this HPA or heated plate accelerometer in more detail, and we have seen that the proof mass in this kind of device is suspended by a thin cantilever. Okay. So, this another type of accelerometer is HGA. That heated gas accelerometers. So, heated gas accelerometers. Okay. Heated gas accelerometers can be of different type. Okay. They can be open loop type or they can be closed loop type. Depending on the axes along which it is measuring acceleration, it can be a single axis, bi-axis and tri-axis accelerometers. Okay. So, when I say open loop, it means that there is no feedback in the open loop type of HGA, okay, where they relies on thermal convection shifts only. Okay. Then closed loop kind of HGA are where feedback systems maintain the gas bubble position. We will see what I am talking about, what is the gas that I am talking about. Okay. And this closed loop, like any other system, offers better reliability and better sensitivity as well. Okay. The accuracy and other sensing parameters is enhanced when you use a closed loop kind of HGA. Okay. And depending on the axes that I have just mentioned, you can have different designs, and along with that number of heaters and the sensors that you are trying to build actually increases. Okay. We will see at least with the example of a biaxial kind of HGA, so that both can be understood, like single axis and tri-axis kind of HGA can be understood. So, we cannot discuss all, but at least we will discuss one of them, particularly the biaxial kind of HGA. Okay. So, the difference between HGA and HPA is that this heated gas accelerometer uses gas as a seismic mass, not the cantilever or a proof mass attached to a cantilever. Okay. So, what essentially you are using is you are using gas itself inside some cavity which is sealed by some hermetic sealing. Okay. And this gas is itself is being used as a proof mass or inertial mass. Okay. So, usually these gases are low thermal conductivity gases. It can be a simple air, or mostly these are CO2 or argon gases. Okay. This HGA can be fabricated on a micro machined CMOS chip and is complete biaxial motion measurement system. Okay. Of course, you can have a triaxial measurement also, but mostly this biaxial kind of devices are very popular. Okay. The principle of operation of the device is based on heat transfer by forced convection. Okay. So, we have seen different ways of heat transfer. If you remember, it can be by conduction, it can be by radiation or by convection. Particularly for fluids, we have seen that conduction and convection are two important methodologies. Okay. Convection can be natural, which is caused by gravity, where hot air actually go up. Okay. And it can be a forced convection also, which is actually by which this force is actually comes by applying an artificial external force. Okay. Or this convection is actually being achieved by some artificial external force, for example by using a blower. Okay. By this forced convection, you can produce a certain kind of acceleration, and this is the backbone of this heated gas accelerometer. The forced convection is the fundamental reason behind this HGA. Okay. We will see how forced convection leads to this kind of accelerometer. Okay. The sensor measures the internal changes in the heat transfer of the trapped gases, and these gases I have just mentioned are thermally conductive gases. Okay. It is equivalent to traditional inertial mass accelerometer, except that you are using gases or this low thermal conductivity gases itself as a proof mass. Okay. So this inertial mass that I am talking about, these gases, they are basically thermally conductive, but at the same time it is thermally non-homogeneous in nature. Okay. The gaseous inertial mass provide some advantages compared to the traditional solid inertial mass, although looks very similar, that in place of using a solid mass you are using a fluid in the form of this thermally conductive gases, but the advantage of this kind of device is tremendous. Okay. The most important advantage is a shock survival, and this shock survival goes to like 50K gravitational force, okay, leading to a significantly lower failure rate. So in the place you can understand that, say, if your accelerometer was built to sustain a acceleration of around say 100 G, okay, and in place of 100 G there is certain force which is exerted on this, and suddenly the acceleration goes to 50K, okay. In that places this kind of device is very helpful. If you see it carefully, if you apply on a cantilever based proof mass, okay, in place of 100 G, if you apply say 300 G, okay, or 3000 G in fact, okay, say more than 30 times, this device is going to break, okay, or there will be permanent deformation in it or something else, this device will not work, okay. But that is the advantage of this heated gas accelerometer, that even you apply a larger force, or if the proof mass is subjected to a larger acceleration, it will not get damaged, okay. They are built to sustain larger shocks, okay. Now let us have a figure of this, or a concept of this heated gas accelerometer, okay. As I have mentioned that this is micro machined from silicon itself. So this figure, figure A, shows the cross sectional view of the HGA sensor, and only one axis is shown over here, that is x axis, for example, okay. You have a silicon substrate, I will come to this trench, okay, but you have two thermopile junction. I will talk about this thermopile in a while, and then you have this gas cavity, and in this gas cavity a heater is placed. Mostly these heaters are resistive heaters, okay. Now here is the heater, and gas is filled inside this gas cavity, which is hermetically sealed, okay. Now this heated gas, if you see, the temperature profile is symmetric around the heater, okay. And you can understand that this type of temperature profile can be understood from this kind of HGA, alright. Then when you apply a acceleration, this causes this heated gas to shift to the right or left, depending on how this system is getting accelerated, okay. Or if you don't talk about system, at least the proof mass or the inertial mass, which is in the form of this gas, is shifted, okay. Right now I am accelerating it into this direction, means the heated gas will shift towards the right, okay. Because of that there will be a temperature gradient. So initially the gases at these two edges were equal, now they are not equal. Now the sensor contains a micro machined plate adjacent to a sealed cavity filled with the gas that we have just seen, okay. Now the plate has an edged cavity, or a trench is formed in it, okay. Now a single heat source, mostly resistive, okay, which is centered in the silicon chip, is suspended across the trench, okay. Now 4 different temperature sensors, mostly in the form of thermopile made up of aluminum or polysilicon, are placed symmetrically around the heater, okay. So depending on how many axis accelerometer it is, be it a single axis or biaxis or triaxial, you have that number of pairs of thermopiles, okay. So if it is a single axis accelerometer, you have a pair of thermopile, one in this place and another in this place around the heater, placed very symmetrically, okay. If it is a biaxis, you have another this kind of trench formed here, and 2 thermopiles are placed over there. So total number of thermopile pairs are 2, okay. And similarly for triaxis, you have 3 number of pairs or 6 number of thermopile placed, okay. So thermopiles are located equidistantly on all the 4 axes of the heater source, if you are talking about dual axis HGS. Okay. A thermopile measures only a temperature gradient that we already know. It doesn't measure the absolute temperature. So the left portion is the location of the cold junction, because your hot gases has moved in this scenario. Okay. Then the right portion is for the hot junction. So it measures the difference between two junctions. All right. The purpose of using thermopile instead of a thermocouple is only to increase the electrical output signal and not anything else. Okay. You can also have thermocouple in place of thermopile, but then your signal levels will be low and you will need another layer of amplification to read these signals. Okay. So two pairs of the junction is for measuring, and a thermal gradient along the two axes, x or y axis, is available. Okay. Now under zero acceleration, when there is no acceleration at all, a temperature distribution across the gas cavity is symmetrical about the heat source. Okay. Therefore, the temperature is same at all the four thermopile junctions, causing each pair to give output as 0 voltage. So if I talk about this sense where I am talking about only one axis, okay. So if the temperature read by this thermopile, say J1, and thermopile J2 is say T1 and T2, okay, the difference between T1 and T2 is 0. Okay. Although the profile of heat along this heater, it will be maximum. Okay. So the profile will look something like this, but if I talk about T1 minus T2, it will be 0, because they are at equal temperature. Okay. Now when it is accelerated towards left and the hot gas is accumulated in the right, now the profile is not symmetric. Okay. Now this T1 is at colder junction, while T2 or J2 is at higher temperature or at the hot junction, means that definitely T2 is higher than T1. Okay. So T2 minus T1 is definitely greater than 0. All right. Now the heater is warmed mostly to a temperature that is well above the ambient, and for this CMOS kind of configuration where you have used it, you have made it on CMOS platform, typically you can reach a temperature of 200 or 250 degrees Celsius, and that is more than enough to heat gases like argon and carbon dioxide. Okay. Now this figure shows two thermopile junction for sensing the temperature gradient along a single axis, and the same you can imagine for bi-axis. Okay. Now gas is heated so that it is hottest near the heater and rapidly cool down towards the left and right temperature sensors, which is our ideal case. Of course, it will not be, there will be gradients and it may not be following this particular graph, but for the simplicity we are assuming this. Okay. When no force is acting on it, temperature has a symmetrical cone-like distribution that we have just seen. Okay. Now when temperature T1 at left Tp is equal to temperature T2, acceleration in any direction, as we have discussed, will increase or decrease the temperature. Okay. And the temperature profile will change. Okay. Under the acceleration forces, the warm gaseous molecules shift towards the right, if right thermopile, if the acceleration is in this direction, and in the reverse way it will come to J1 if the acceleration is in this direction, and that is how we have seen that the T2 minus T1 is greater than 0. Okay. Now this difference T2 minus T1, okay, the differential temperature delta T, which is T2 minus T1, can give us certain idea about the acceleration. Okay. So the voltage at the thermopile output becomes directly proportional to the acceleration, or at least the difference between the thermopile's temperature at least gives you the idea about the acceleration, because this change has happened because of the external force applied. Okay. There are two identical acceleration signal path on the device, one to measure acceleration in the x-axis in this bidirectional or bi-axis accelerometer, and one to measure the acceleration in the y-axis. Okay. The HGA, this kind of device, is capable of measuring acceleration with a full scale range from even less than 1 g and anything above 100 g. Okay. However, for shock and other things, you have seen that it can absorb a shock, very highest level of shocks, and acceleration of the order of 50,000 G is also possible with this kind of devices. Okay. So the advantage of HGA is this kind of device can measure both dynamic acceleration. When I say dynamic acceleration, I means mostly vibrations, and it can also measure the static acceleration or gravity. Okay. Because if I talk about vibrations, okay, the cooling and heating cycle of these gases should be very fast. All right. Because some gases is moving in this direction when acceleration is in this direction, and then it should rapidly cool to again to the normal temperature, or it should come in the temperature range of this particular profile, or this cone kind of profile. Okay. In those cases, you can measure the vibration very easily, and that's why these gases are thermally conductive but low thermally conductive. Okay. Fine. So the analog output voltages from this kind of HGA chip is available either in the form of absolute mode, or you can also get output in the form of ratiometric mode. Okay. The absolute output voltage is independent of the supply voltages, while the ratiometric output voltage is proportional to the supply voltages. Okay. And the typical noise floor is something below 1 mg per hertz, and this allow sub milli G signals to be measured at very low frequencies, and that's why this HGA devices are very popular, and it is mostly patented by one or few companies only. Okay. For HGA sensor, the output sensitivity changes with ambient temperature. Okay. And that is something we do not want. Okay. So a typical sensitivity change for HGA device is shown over here, where you can see that a plot of normalized sensitivity versus temperature is given for a HGA for the sensitivity for the ambient temperature. Okay. And you can see that the sensitivity decreases when the temperature increases, means at lower temperature, okay, their sensitivity is good, but when you keep on increasing the absolute temperature of operation, its sensitivity decreases. However, they can be calibrated, because mostly these devices are linear sensors only. Okay. And they have a number of advantages, like the biggest advantage is there is no moving part. So it's only the gas which is shifting its position from right to left depending on the situation, how the device is getting accelerated. Okay. And the fabrication is also not very complicated. They are low cost and easy integratable kind of device with CMOS technology. Okay. And they can, since no cantilever or no say suspended mass kind of structure is there, they can have high shock resistance. Okay. And they can operate in high vibration environments. We have seen that it can withstand acceleration of the order of 50,000 G. Okay. However, there are several limitations also associated with HGA, like their response time is slow if you compare it with any piezoelectric or capacitive accelerometer, which makes half of the accelerometer in practical. Okay. They are sensitive to temperature. We have just seen one curve for sensitivity versus ambient temperature. Okay. And their bandwidth is limited. Okay. However, for piezoelectric devices, the bandwidth is very high, okay, or at least decent as compared to the HGA devices. Okay. Their power consumption is really high, okay, because of the continuous heating of the heater. Okay. So this heater, even if the device is not in acceleration, this heater is always on, because we are always ready for some external force to be applied. Okay. So because of this always on heater kind of thing, the power dissipation is typically very high. Okay. So however, the advantages are numerous. So their applications are also very wherever you need very precise and very high level of shock, you expect that kind of application you can extend for this kind of HGA devices. Okay. Then this is all about the thermal accelerometer, but then you have another category of accelerometer which is getting popular, particularly with the rise of quantum electronics or quantum mechanics. You have tunneling accelerometers. Okay, tunneling accelerometer, as the name suggests, there is a phenomenon of tunneling associated, okay, or electrons tunneling is associated. If you do not know the tunneling phenomena, I will suggest that you read any good book on semiconductor devices. What we are going to do is we will be directly using the concept of tunneling over here. Okay, so a tunneling accelerometer is a type of nano or MEMS, part of NAMES or MEMS system that uses quantum tunneling current. Okay, so they are extremely sensitive to minute displacements. Of course, we have seen that these displacements are actually the cause of the acceleration. So they are extremely sensitive to minute displacements due to the exponential dependence of the tunneling current on the gap size. Okay, the gap, this current is highly dependent on the gap size. We will see what gap sizes I am talking about. Okay, what is the range of gap size that I am talking about. Okay, now in the HGA we have seen that there is no proof masses actually. We have used the gases itself as a proof mass. Okay, but except that in all other cases of accelerometer we have seen that there is a concept of proof mass. Okay, in fact, if you see in the HGA also we have seen that at least gas is there and gas itself is being used as a proof mass, right. So in this kind of device also, in the tunneling accelerometers also, you have a proof mass. Okay, so a proof mass is suspended over a sharp conductive tip. Okay, the distance between the mass and the tip changes with the acceleration. Okay, now quantum tunneling current between the tip and the mass varies exponentially with the displacement. Okay, and this current is measured and related to the acceleration, and that is how a tunneling accelerometer works. Okay, let us have a quick layout of a tunneling accelerometer. Okay, you have a nitride cantilever and tunneling tip associated here, and then you have a squeezed film damping holes. Okay, and you have a deflection electrode and a proof mass electrode and a hinge. Okay. Now, electron tunneling can only be observed when the gap between a pair of clean metal electrodes is nearly of the order of 10 angstrom. Okay. So, I am talking about now, till now we have seen mostly in devices of the order of where you need a feature size of the order of micrometer or nanometer, and this kind of tunneling accelerometer even go beyond, and tunneling phenomena as you know can be observed at very small distances. And in this kind of device, tunneling accelerometer, we need the electrodes, particularly this electrode and the deflection electrode and the proof mass electrode, to have a gap of not more than 10 angstrom. We are talking about that kind of level. Okay, so that is why I have mentioned that the electrode should be ultra clean. Okay, and they can be observed or they can be fabricated in clean room of class 10 or class 1 kind of structure, okay, of the class. Okay, when there is an acceleration, proof mass moves, due to which this nitride cantilever is deflected. Okay, so when there is an acceleration, the proof mass is moving, and because of that the nitride cantilever will deflect. Okay, now this deflection changes the gap between the tunneling tip and the deflection electrode. So you have the deflection electrode. The proof mass electrode is indirectly responsible for changing in the gap between the tip and the deflection electrode. Okay, right. Now the tunneling current, which is sensitive to this particular gap between the tunneling tip and the deflection electrode, changes proportionally to the acceleration. All right. Please note that the operation of the tunneling accelerometer requires a feedback control circuit to maintain a constant tunneling gap between the tip and a counter electrode. Okay. Now the relationship between the tunneling gap and the tunneling current is given by this tunneling current is directly proportional to the tunneling bias voltage into e power minus alpha 1, where this alpha 1 is a constant and is given by 1.025 into A inverse EV inverse, okay, into under root phi xtg, where phi is the effective height of the tunneling barrier or the effective work function, and this xtg is the shortest tunneling gap between the tunneling tip and the proof mass electrode. Okay. This kind of device has various advantages, like they have ultra high sensitivity, and when I say ultra high sensitivity means they can actually detect a sub nanometer kind of displacement. Okay. So mostly required for the quantum applications. Okay. They are ideal for low frequency and low noise applications. Okay. And they can be miniaturizable using NIMS technology. Okay. And their power consumption is not very high. Okay. These devices are ultra low power devices. Okay. However, they have various limitations also. The first limitation that comes from the requirement of the clean room and the complexity associated in the fabrication of this kind of device. Okay. Then they are sensitive to temperature and environmental fluctuations, because you have seen that gap of the order of 10 angstrom and below are involved. Okay. So they are susceptible to this kind of environment fluctuations. Okay. The tip mass configuration is fragile. Okay. Particularly if you see, lot of cantilever structures are required. Okay. The nitride electrode, if you see in this, you have nitride cantilever, you have deflection electrodes, proof mass electrodes, tunneling tips, so many things are involved which are fragile basically. Okay. Then they have limited dynamic range compared to the existing devices like capacitive devices. Okay. So with this, I think we have finished this module on discussion of accelerometers. Before we discuss the accelerometer, we have talked about other devices also, like displacement sensors. Okay. This displacement sensors, velocity sensors and accelerometers, they are all interrelated by the derivation and integration of the position. However, we have seen that for particular cases, for particular requirement, sometime you need that particular kind of sensor. For example, acceleration can be found from its position. Okay. However, you require accelerometer because all the time you cannot use the displacement sensor, particularly with the condition of noise and other things. So with this, we are finishing our module 10. We will talk about other kind of sensors, particularly from the application point of view, like smart building sensors and some sensors on healthcare in our module 11 and module 12. Thank you.